my name is Nima, and I'm going to be presenting our research on performance modeling of serverless computing platforms. I'm a PhD student at the University of Alberta, and this research has been done in the Performant and Available Computing Systems, or PACS labs in York University. My co-author is Dr. Hamzeh Khazaei, which is also my supervisor. So first we're going to have an introduction to what we're doing today and what our performance model is capable of. And then we will talk about the description of a system that is being modeled by such a performance model. And then we will talk about an overview of how our analytical modeling is done. And then we will see the experimental validation and conclusion of the work. So first up, introduction. Service computing, which is the newest paradigm in cloud computing, is some way of enabling computing in a way that runtime operation and management is completely done by the provider. So this reduces the overhead for the software owner and allows you to delegate all of the provisioning and scaling of resources tasks completely to the cloud provider. In this way of doing deploying new services, software is developed by writing functions, and they have well-defined interfaces along with functions that are being deployed separately, so they work separate of each other, and each of them have scaling units of function instances. So the way that the development would go in such a platform would be that you as a developer would need to upload your code to AWS Lambda, or you write code in the Lambda's code editor, and then you specify a trigger or an event that executes your code. And then whenever that event happens, the serverless provider, which is in this case AWS Lambda, for example, would execute your code. It will automatically patch it. It will automatically scale the resources allocated to it when the demand goes up and down, and you only pay for the compute time that you use. You do not pay for the provisioned capacity. And so this service computing holds a lot of great promises, but the current model has a lot of shortcomings as well. For example, there is no performance guarantees, and everything is done in best effort basis. And this is mainly because in serverless computing, the number of function instances, which is basically the number of servers, is dynamically changing all the time. And most of the literature in the performance modeling of cloud applications cannot assume or deal with this kind of dynamic change in the number of servers. So no work has done this kind of thing before, and accurate performance modeling can be beneficial in many ways. For example, using this modeling, you can ensure the quality of service, you can improve the performance metrics, you can predict or optimize your cost, especially the infrastructure cost that the cloud provider is incurring, and you can move from best effort basis to performance guarantees. It can basically benefit both serverless providers and application developers in that sense. So let's see our system description. So in this section, we're going to introduce the description of the system that is being modeled here. So any serverless computing platform that abides by these rules will be modeled by our performance model, and most of the current generations of mainstream serverless computing platforms will be modeled by this because they have similar auto-scalings. So we assume 3 states for each of the function instances in the pool of resources dedicated to each function. And the first one is in the initialization step, where the function instance is still performing initialization tasks like preparing the virtual machine and then deploying container onto it, downloading the developer's code. And such tasks are being done in this space in this time zone. And in addition to that, we also have the application initialization task, like downloading something from the S3 bucket, or for example, making connections to the database. We have the running state, which is when the instance is performing the tasks that are required to process a request, an incoming request. And we have the idle state, which is where we have a provisioned state that is not running any workloads and is just sitting idle. And we also have the notion of cold start and warm start requests. When we don't have the provisioned capacity to handle a new request, that request will need to wait for the serverless platform to instantiate a new function instance. And it's going to have to wait for the function to be initialized and then execute the tasks that are needed to handle that request. So this is what we call the cold start request, and it's longer. The request takes longer to fulfill compared to a normal request where we have provisioned capacity and we have idle servers that just need to execute the tasks that are required to process the request, which is what we call a warm start request. So to look at the autoscaling in serverless computing platform, we have to look at both actions of scaling in and scaling out, because autoscaling in serverless computing platforms is done horizontally. And so scaling out is when we add new function instances to our pool of resources. And this picture on the right shows how scaling out is happening. We have a pool of warm function instances. And if all of them are busy running a task, or maybe we haven't received any requests, so we have terminated these instances and we don't have any servers in our pool, in that case, we're going to have to block the request from going to our warm pool due to lack of idle function instances. And then that request will end up being a cold start request, which causes the creation of a new function instance. And if we have reached a maximum level of concurrency, that is the maximum number of servers that the serverless computing platform will allow your function to have, that request is going to be rejected. That's for the scaling out action. For scaling in action, imagine after some time the demand for function has gone down, and some of those function instances are not going to be receiving any new traffic. So in that sense, after the server has processed its last request, which takes service time amount of time, after some specific threshold, the serverless computing platform will destroy that function instance. And this is what we call an expression threshold in our paper. And this is fixed for all of the current mainstream serverless computing platforms. For example, it's 10 minutes for most of them. For example, for AWS Lambda or IBM Cloud Functions, for Google Cloud Functions or similar systems. And it is set to 20 minutes for Azure Functions. So this is mainly fixed at the moment, which is something we're going to discuss later on. So this brings us to our analytical modeling. Our model, which is depicted on the left, is basically a Markov chain. And this basically shows the state of a warm pool of resources, and each state represents the number of function instances that we have in our warm pool of function instances. And so we have some rate for adding new functions, which is due to cold start, which is what we discussed earlier. And we also, to calculate the rate of cold starts, we're going to have to assume that this is similar to an Erlang loss system, and or an MGMM queue, and we can calculate the different rates from that literature. And to get the rate of expiration of function instances, which is when we expire an instance, terminate it, and then free up the resources that it has been consuming, we need to take a look at the life cycle of the function. And we have the calculations in our paper, but we cannot go through all of the details here. So for each state, we can also calculate the probability of rejecting a request, which is very important because you want your service to be always available to your users. We want the probability of cold start, and basically this shows us the level of quality of service. For example, we can calculate the average response time using the probability of cold start, which is what is the probability for an incoming request to have to go through the process of cold start. We can calculate the mean number of instances in our warm pool, and those instances can either be in running state or idle state. And if they are in idle state, they're just deployed provision capacity that is not being used at the moment. So this brings us the notion of utilization, which is the ratio of instances that are running some task instead of just sitting in our warm pool. This basically shows us how much of the deployed capacity is actually being used at the moment. Now, for experimental validation, we use AWS Lambda. We deploy the function with a mixture of CPU and IO intensive tasks. And it was on the Python 3.6 runtime with 128 megabytes of RAM, which is actually not important for our performance model, because we only need the average cold start and warm start response times. And if you change the memory configurations of your function instance, it's going to affect those numbers, and it's automatically going to we are going to see their effect automatically in the performance model. And we performed all of our experiments on US East 1 region. The client was Virtual Machine and Compute Canada Arpetos cloud system with 8 virtual CPUs, 16 gigs of RAM, 1 gigabit per second connectivity with single-digit latency to AWS servers. We used Python for the client, and we used our in-house workload generation tool, which is called PaxWG. And we also used the official Boto 3 library for API communication to be able to communicate with the Lambda API directly without any intermediary interfaces like API Gateway, because we didn't want the performance fluctuations in API Gateway or any intermediary platform to have any effect on our results. Because cold starts were so rare, we had to run our experiments each for 28 hours, when we also calculate the standard errors, which are the vertical bars on the left that you can see. And as you can see, the results of our experimental results are aligned perfectly with the predictions of our performance model. And for example, here you can see the probability of cold start for different arrival rates. And for larger arrival rates, the cold starts become very rare. So that's why we had to run experiments for such long times. We also see the utilization, and as you can see, as the arrival rate goes up, the probability of cold start will go down, and we will have better utilization in terms of how much of our resources are we actually using. So we performed some what-if analysis for some sample workloads, and we gathered these workloads from literature, and they are, for some of them, cold start and warm start are close to each other. For some of them, they are very different. We used a range of different workloads to show how the results would differ for different workloads. These are the probability of rejection for different arrival rates, and as you can see, this basically gives us the capacity of the system. So the application developer will know in advance what is the maximum arrival rate that they can handle with their current setup. And this is a very important aspect that is very hard to calculate using experiments. It's very expensive, and it's going to take a lot of time for them. This is another part where expiration threshold is basically fixed in all of the current mainstream service computing platforms. But what we're suggesting here is that what if we could adapt this expiration threshold to different workloads? And as you can see, the effect will be very different for different workloads. For example, for this workload, we see that the performance would differ a lot when we change the expiration threshold. But for example, for W1, which is this one, we don't see a lot of difference in the performance, but as we increase the expiration threshold, the utilization always goes down. So maybe the serverless platforms using such models can adapt this value and improve their utilization without sacrificing a lot of this application performance. So in conclusion, accurate and tractable analytical performance model is something that is being suggested in this work. And this model will give us the ability to predict important performance or cost-related metrics. It can predict quality of service. It can benefit both service providers and application developers. For service providers, it can give them the ability to predict the quality of service and optimize give them the ability to optimize their infrastructure costs, knowing how much it would affect the performance of the application. It could also help the developers predict how their system will react in different workloads and help them optimize their memory configuration to occur minimum cost and that satisfies the performance required metrics. And making the expiration threshold adaptive could maybe allow us to have better cost performance trade-offs. So this is an overview of what we discussed today, and you can also see the website for my research and my Twitter in case you want to contact me. Thank you very much.